I'm going to be telling you about joint work with Dave Humboldt. So dropout, as you may know, is a technique for training neural networks where the algorithm uses stochastic gradient, otherwise known as backprop, except before each iteration, it removes a random half of the nodes in the network. Then it makes the update, then puts those back, removes a different random half, and so on. So after it computes the value of a node that was kept, then it scales it up by an amount that sort of makes up for the fact that it had a chance to be removed, so that the expectation of the output of any node, if it had the same inputs, will be the same as before. So you can think about the effect on each node as kind of noising the output. So dropout is a very simple technique, but it significantly improves the accuracy of training of models produced by the learning algorithm. And so it's commonly used. So it's included in all of the most popular neural network packages. The algorithm was introduced in 2012, but the paper describing the algorithm already has about 3,000 citations. So Dave and I wanted to study it because of its popularity, its usefulness, and because of the fact that it's surprising that something like this should improve accuracy so much. So we want to understand its properties. So we have to start somewhere. So the first thing we decided to look at is how does using dropout affect the inductive bias of the algorithm? So put another way, when you use dropout, how does this change the learner's prior preference over which models it likes to produce before it's seen any data? So this paper is about this question in the context of deep networks. Two previous papers studied this question for networks without any hidden layers. Our analysis is about networks of rectified linear units. So each one of these units takes a linear combination of its inputs and then composes it with a function that's plotted there. It's sort of plotted there. We're analyzing what you might call a standard deep network architecture. So you have a certain number of inputs, you have a certain number of hidden layers. Each hidden layer has the same number of hidden nodes, and each layer is fully connected with the next layer. So here's a little bit of quick notation. K is the number of inputs, N is the width, D is the depth. We'll refer to the parameters collectively as script W, and the function computed by a network with parameter script W is F sub W. So the dropout pattern is this binary valued, vector valued quantity that describes which nodes are kept and which nodes are removed. So for a given collection of parameters and a given dropout pattern, we have a function, right, that is obtained by applying the network with those parameters, but anytime you encounter a node that's been removed, you replace its output with 0, and otherwise you compute as usual. Our analysis is focused otherwise in the following way. We'll only consider dropout probability of a half, but that's the most common choice. And we're going to analyze the quadratic loss. So the goal of the algorithm will be to produce a model that has a small risk, which is the expected quadratic loss. So next is the dropout criterion. So when an algorithm is using dropout, you can think of it as attempting to minimize this quantity. So specifically, dropout is a stochastic gradient algorithm with respect to this objective function. And the objective function is the expectation for a random example and a random dropout pattern of the loss obtained by applying the dropout pattern to the function to the network, and then applying that function to the input and looking at its loss. So if that's what the algorithm is trying to optimize, you can think of it as effectively doing some sort of regularized learning where there's a penalty for each weight vector. Because you might expect that when you add noise, right, to the computation of a function, you're going to make its expected loss worse. And so the value of the dropout criterion is going to be larger than the risk. And the difference is how much less likely or how much you dislike to use that function. Okay, so in this work, I told you we wanted to focus on inductive bias, and so we're abstracting away the error due to random sampling by studying the optimizer of the dropout criterion with respect to the underlying distribution. Right, so you can think of this as focusing our attention on the bias part of a bias variance decomposition of the generalization error of an algorithm. There's another way to look at it, though. If you apply our results on distributions that are concentrated on training examples and assign equal weight to each training example, then our analyses address the question of what kind of training sets is dropout willing to fit, and what will it give up on. Okay, so the first result I'd like to tell you about formalizes the statement that dropout is scale-free. And so what exactly is it? So let's let P be any joint distribution on input-output pairs. And then let's form Q by modifying P by rescaling each of the inputs. Let's say I'm measuring an input using meters instead of inches, or Fahrenheit instead of Celsius, and so on. So what the statement below says is if you minimize the dropout criterion with respect to the new distribution, and then evaluate it with respect to the unpenalized loss with respect to that distribution, you get the same value as if you had done the same two steps with the original distribution. So the quality of the model trained by dropout is equally good before and after rescaling the inputs. But this is definitely not the case in a very dramatic way for let's say, weight decay, otherwise known as Tikhonov regularization. So the second result I want to tell you about has to do with non-decreasing neural networks. So, a non-decreasing function is a function where if you increase one of the inputs, it doesn't decrease the output. And so a particular node is non-decreasing exactly when all of its weights are non-negative. And if you build a network out of these non-decreasing nodes, it also is non-decreasing. So if you train a network with data that's consistent with the non-decreasing function, you would expect to produce a network with positive weights. As a matter of fact, we thought that this was true, and we were trying to prove it as a lemma for another analysis. But it turns out it's not true, even in a very simple case. So suppose we build a distribution that's concentrated on just two examples. One example with all 0 inputs and a 0 output, and another example with all 1 inputs and a 1 output. So if you have enough hidden nodes, the minimizer of the dropout criterion actually must use at least one negative weight. So why is this true? Well, if you have all non-negative weights, then if you fit the data, you have to have a lot of variance in the output. So the reason is you're going to have a lot of variance in the input because of the effect of dropout on the inputs. And then the fact that you have all non-negative weights means that that variance that you have in the inputs gets carried to the output. But if you have some negative weights, you can reduce the variance at the first hidden layer, effectively answering the question, do I have any ones at all on the input? So here are a few quick other results. So the dropout penalty can grow exponentially with the depth, whereas any norm-based regularizer must have a penalty that grows linearly with the depth. So then there are a few differences between dropout in the deep network case and the shallow network case. The dropout penalty actually can be negative. It can be non-monotonic in the dropout probability, and it can depend on the labels. So that's all I'm prepared to say. Thank you for listening. Question? Yes, please. No, I'm not aware of anything fundamental. We just started with that, and we never went on from there.
binarize them. So you had to, if you had an input between 0 and 1, you had to kind of flip a coin to turn it either a 0 or a 1.
Wow.
So it wouldn't kind of naturally work with the scale of the inputs if you had different scales inputs there. I was wondering if there's anything like that you've seen.
That's interesting. I mean, that runs counter to the analysis I told you about, where dropout is scale free. So there must have been something about our context that were different. Yeah. So I guess in our analysis, if you rescaled one of the inputs and kept the others the same, that shouldn't have an effect on the quantity that we analyzed. So I'm curious to hear how how the scale affects your proofs.
Okay. Thanks, Phil, for